All right. So today we're going to be working on documenting LucidMQ. Um, we have a website here. It's up. It's kind of shitty. It has some definitions or like conceptual things around LucidMQ for now. So what I'm thinking we're going to do is go into the repo, just start documenting all these methods, and then we can run the Rustbook extractor to extract this to Markdown, and then we'll have all the stuff on the website as Markdown. So it'll give us a good intro into defining like what are these underlying packages and what the exact functions do. So let's go ahead and just start. Um, the first the first library we're going to look at is Nolan, and this is the underlying storage of LucidMQ. So if we look here at the README, just quickly, briefly goes over what it is. It's a very simple write-ahead log or commit log implementation that exposes an API for appending and reading messages from the commit log. That's pretty much all it does. It's also a little bit smarter because it can automatically clean up logs that are like that contain data that is either too old or too big. So we'll just go to this. This is the commit log itself. So we have a definition for our structure. Commit log is just a structure that stores logs in memory on disk. We'll go back to this in a second when we start discussing the segments. But it's ultimately all it is it's a directory that is made up of two different types of files, logs and indexes. And these logs and indexes are stored within a directory, and that directory makes up a commit log. So we have our constructor here, which is new, takes in a base directory, which is a string reference, the max segment size, and the max bytes of the commit log. So that's already documented, so we don't need to go any more to that. We have our append method, which is publicly exposed. So when you want to add an entry to the commit log, you're going to call append, and what that does is it appends those bytes to the latest segment, which is stored, and if it doesn't fit in there, so let's say our max segment size is about 100 bytes. We're at 90. We give it a new message of length 20. That doesn't fit into our 100 size segment size. So what we're going to do is we're going to split the segment that the latest segment is going to be flushed onto disk, and then a new segment will be created, and then that new 20 byte message will be on that new segment. So I think this is what that says here. Okay, cool. Okay, so load segments. So this is called during startup. We have a lot of files that are stored on disk, and we want to be able to recreate this commit log on startup so we can quickly access like where to append to and where to read from given a certain offset. So what this does is it iterates through the directory, finds all of the log and index files, and creates segment entries for them for the commit log. It also will remove any, let's say, corrupt files. So files that, if there's a log file or a index file that doesn't have a matching log or index file respectively, that's going to be deleted. Cool. Get max segment size. So this just returns what is our max segment size of the commit log. Reload segments. So it may be useful to look through the directory and update if segments haven't been, yeah. So it's going to look through the directory and update if segments that are not loaded into memory get properly loaded into memory. Split. So this is the helper method that we were talking about earlier when we're appending on bytes that won't fit into a segment. So what it does is it just goes ahead and flushes the current segment and creates a new segment, a new current segment. Goes ahead and calls reload. Read. This is the other basically main method that any user is going to use when using this library. So given an offset, we're going to return the entry from the commit log. I guess we'll go into more about like, well, what is an offset when we start talking more about segments. Clean. So we have a cleaner method which is only right now supports max size, but it will probably be expanded later to support timing-based like entries. So right now, if you give a max size for the commit log, and if that commit log starts to exceed that max size in bytes, then we're going to go ahead and just start cleaning up the oldest segments. This right here, we'll call that, and then do the cleaning for us. Return the oldest offset. This will return the oldest offset in the whole commit log. Useful for when you're working with this thing if you don't know what the oldest offset is. And then the latest offset, pretty similar, except the latest entry that was pushed in. All right, so high level, we kind of understand what a commit log is. So let's go ahead and drill down into segments. So we have two different types of segments. We have a virtual segment and a regular segment. So so the segment, regular segment, is a segment that is actually stored on disk. So this actually represents that index file, that login index file that are actually stored on disk. Whoops. All right. Now a virtual segment, the latest segment uses a virtual segment, and this is just a memory representation of a segment that is just stored in memory. So this allows for very fast access of the current segment, and it's intended for speed purposes. So that's why we have two of them. So let's go ahead and add that here. A virtual segment is a that holds Okay, we probably don't need to verify OneDrive. Let's see. Only for the current segment. And that is to allow for fast access for data in that segment. And so why do we make this design decision? This is because when you have consumers consuming from the segment, generally they're going to be kind of polling at the end there, waiting for like fresh data to come. And so we want this latest data to be stored in memory so we can serve it faster instead of having to make an OS call and go to disk to grab it. So that's why we're going with a pattern like this, even though it may drive up the complexity a little bit. I think that the speed trade-off is worth it. So, okay, so we have our constructor here, new. So it just creates a new virtual segment with the provided starting offset and max segment bytes. Okay, so what is an offset? So an offset represents an entry of data in the segment. So there are two, I guess, different types of offsets. We have the offsets represented across the whole commit log, and then we have like the relative offsets within the segment. And so this virtual segment needs to know what is the starting offset, like what is the starting offset of this virtual segment relative to the entire commit log. And that allows us to keep track of, or that allows us to keep track of when we make a query for a certain offset, we know whether it falls into this segment or other segments or not. Okay. Okay, load segment. So this is called when we given a directory. What even calls this? What the hell? Okay, segment, load segment. Virtual segment, load segment. Okay, so this looks like given a okay, so it looks like so on startup when we look through the directory, we have to build these segment files for like the memory representation for access. So, and so the commit log is going to call this when it calls load segments. It's going to find all the segments, and then on the latest segment, it is going to create a virtual segment. And this is what loads that into memory on startup. Load a new segment into memory. Okay. Right. Okay. Okay. So as you saw earlier, when we have that method, publicly exposed method called append in the commit log, and what that does is basically after it verifies that the current segment can hold the message, then it's going to call write on the segment. So, and so this is what actually does the write. We take in our data that's passed in from our commit log, and then we do some checks here to verify that uh, that that the data isn't greater than maybe the size of the segment, the total size of the segment, or that it won't exceed the max segment byte size. Um, After those checks are done, it does a write, and since this is virtual, we're writing it to a cursor, and all a cursor is it's just like a vector of bytes, and um, and those bytes are just represented in memory. So we're just going to do a write to the in-memory buffer, and then we're going to do some fun calculations here of what the next offset is and what the current position is to um, allow for easy writes and reads um, for the next calls. Then we have read at. This is so when commit log calls read, what it does is it gives an offset, and it gives an offset, and then if it knows that the offset is in this segment, then it's going to go ahead and call this read at function, which does some validity checks to make sure that this offset can actually exist in the segment. And then it does a seek in the buffer to pull out the data that we want. It goes ahead and returns that to our commit log. Flush. Flushes the virtual. So flush just flushes the virtual segment to disk, where it will become a regular segment. This involves two write operations. Writing the log file and writing the index file. Okay. So we have that. Cool. Sweet. Okay. All right. Sweet. So now we are going to go to our regular segment. And so okay, so a segment is the actual, as we said earlier, it's the actual persistent disk representation, or I guess disk representation of a of what's actually being stored. So it's made up of two pieces. Should have probably went over this earlier, but it's made up of a log and an index, which are two different files. A log actually stores the data that you want it to hold, and an index stores metadata about the data of the logs to allow for quick lookups. And these are called entries. So each individual piece of data is called an entry. The actual entry, data, is stored in a log, while the information describing an entry, such as the offset location, etc., is stored in the index. So I think this actually explains that. Um, this we used this before, but I don't think we really need it anymore. We don't really need an actual constructor because our actual constructing comes from loading things on disk. Um, we have so the only way segments are actually created in Nolan is when the commit log calls load segments. So those segments are already stored on disk and they just get loaded into memory. So there's no reason to have like a constructor. So that's why I'm going to go ahead and get rid of that. So load segments. So this is pretty important. So when commit log calls load segments, it's going to iterate through the files. It's going to give it like its directory and then like the segment base. So how does the base work? Good question. Okay. A segment base is the file name that is shared by the log and the index file. And what that is that is the latest, sorry, the current or the sorry, yeah, the offset that is given uh, to this segment to allow for easy. So instead of having to store like metadata about like, well, where does what segment holds what, we could just use the file name uh, to tell us, well, what is the oldest segment, or sorry, what is the oldest offset that is stored in the segment, and then reconstructing the index and also like the log file, we can then determine, well, what offsets are actually stored on this segment. So that's what this segment base actually does. Okay, we read that. Okay, so read that. So when the commit log is looking for an offset that is older than the current segment, it's going to call this readat method, which is just going to do a seek on disk and grab the entry of the offset that is provided. Okay, delete. So this is called by our cleaner method, and it goes ahead and removes our files, deletes the index and the log file from disk. Guess we don't need this anymore. Okay. All right. So now we'll go into the indexes. Pretty similar stuff. So since we have a virtual segment, we're also going to need a virtual index. And an index is technically a piece of a segment. And so our segment files interact respectively with each of their virtual or non-virtual index counterparts. And so this index or these index files manage like it manages either the current or like the current virtual index of so let's see, what do we write here? Okay. All right, I'm gonna go ahead and define it here. So metadata about the segment. It's kind of annoying that it's doing that. I think my computer is just slow. Most importantly, it stores entry for fast lookups. Okay. So new creates a new virtual index. It's a memory implementation where the data is stored in a cursor. Okay. Okay, here we're going to add a new entry to the index. This is the big one here. So when we call read, we need to be able to, so we call read, and read will, so we call read on a commit log. You provided a segment. That goes and looks for the segment that it's stored on. It calls read at in that segment. And then, so this is where the beauty of the index comes in. So this segment doesn't exactly know where this offset is contained. That is actually stored in the index. And so this return entry details by offset will take in an offset, and then it will tell, it'll return the entry information. So where in the file does that entry start, or where in the log file does your offset start? And then B, how big in terms of bytes is that offset or piece of data that you want to fetch? And given those two pieces of information, the start size and the total size, we're able to perform a seek and read from either the disk in terms of like the regular segment or the virtual segment, the cursor, to grab the data that we need. Okay, well, this is actually error handled correctly. Don't really need that. This can throw an exception. If the offset is greater than the size of array, how do we check? Actually, I think we do that above. I remember I was marking around with some unit tests. I think I fixed that. So, very important method. Cool. Flush. This writes the buffered index data to disk. This loads index from disk into memory. Cool. Okay, so this is basically the same thing. This is the same thing, except now we are talking about just the on-disk representation. So just given a file path, we're going to go ahead and create our index. And so an index in these terms is actually an in-memory representation of the entries, as well as a pointer to the file. Okay, we don't need to write anymore. This is done when we flush from the virtual segment. Index from disk into memory. Okay, sweet. Okay, we already went through this. And total bytes. Okay, that's pretty much it. We can go and check out the cleaner. We already talked about this a little bit, but cleaner, just given a retention byte configuration value. Whenever clean gets called, it's going to go ahead and check the directory to make sure that the bytes fall under our retention byte limit. This is our helper function. So I was talking about how we give the segment file's name, so the log and the index, how they match paths. So this helper method actually handles all that for us, as well as gives us some like handy, I don't know, constant variables here. And this could probably honestly be concated. Instead of having 4, we should probably just have 2, but kind of lazy at the moment, so I won't touch that for now. Alright, I'll stop now and then we'll get into LucidMQ.